Right, so what is the proof of this? Okay, the proof that when you do the modulus of z1, z2, you get modulus of z1 times modulus of z2. And when you do the argument of z1, z2, you get the argument of z1 plus argument of z2. In other words, what's the proof that when you multiply two complex numbers together, you multiply the moduli and you add the arguments? Okay, have a go at the proof now, and then just play the video. Okay, right, the proof I'm going to show you, the first one is my favourite one, but it's not the quickest way, because the quickest way is kind of, it's nice, but it's not as interesting. I like the long way. Okay, so what I'm going to do is I'm going to prove it this way. Okay, so what you need to do in any proof really is write down a general expression for each of these complex numbers z1 and z2. Okay, so I'm going to write down this is going to be equal to, I'm just pausing because I don't know what to do. I do know what to do. I'm going to write small r1. Don't do capital R, little r. That was my big question. Doesn't matter, does it? For some reason in class I usually use capital R. I'm not sure why that is. Anyway, so cos theta 1 plus I sine theta 1. So that's a general expression, yeah, for the complex number z1. And there's a similar expression then for the complex number z2. R2 cos theta 2 plus I sine theta 2. Now maybe in thinking about your proof you're a little bit stuck with where to start. That is the difficult thing with maths sometimes, knowing where to start. And that's the only thing that experience can help you with really. When you've seen enough topics or proofs or whatever, you kind of get an idea of where to start. Okay, but as a generalisation, write down an expression for each of the complex numbers z1 and z2. Okay. Now you might have done it a different way and still proved it, that's fine. That's fine. I'm just showing you what my favourite proof is, even if it is much longer than the simplest proof. Okay. Now, let's have a look at what Z1, Z2 actually is. This is where I really could do with a larger board. Okay. So that times that. So it's R1, R2, and then cos theta 1 plus I sine theta 1. You can see I'm trying to squash this up now. And then that's going to be cos theta 2 plus I sine theta 2. Just about squeeze it in, okay? Right, but I'm going to have to start right here now to get the next line in if I can. So R1, R2, obviously, R1, R2. And then here, right, let's expand these brackets, okay? So I'm going to have cos theta 1, cos theta 2. Let's keep on doing the real parts, shall we? So the next real part is when we do that times that, isn't it? And what happens? You get subtract sine theta 1 sine theta 2. Yeah? I'm not going to fit this on one line. It's just so annoying. So anyway, that's the real part. Okay. Next, you're going to get an imaginary part. So I'm going to write the imaginary part down here. In fact, maybe just writing the imaginary part down here is kind of helpful. Okay. The imaginary part is going to be that times that, isn't it? Sine theta 1 cos theta 2, and then it's going to be that times that, isn't it? Yeah. So let's put brackets around that. So that's positive as well. Cos theta 1 sine theta 2. It's incredibly important I make sure that I've got all that correct. Okay? And there's another bracket there to close off. That was not done nicely. That was not done nicely. Okay. There we go. There's another bracket there to close it off. So R1, R2, all of that. Okay, and split it up into real parts and imaginary parts. Okay. Well, what comes next? What comes next? This is the bit I really like. Okay. So notice you got cos, cos, sine, sine. What does that remind you of? What does that remind you of? Okay. Cos A, cos B, subtract sine A, sine B. What does that remind you of? I'm hoping it reminds you of this, cos A plus B, the identity. Okay. What about this one? Sine A cos B plus cos A sine B. What does that remind you of? Yeah, another identity, isn't it? This one's sine A plus B. Yeah? So, how can we write this then? Well, we can write this here, the cos, sine, as that, can't we? Okay, cos theta 1 plus theta 2. And then the I bits, the imaginary part, we write as I sine theta 1 plus theta 2. Isn't that lovely? Okay, I think it is. And let's just rub this off because I just use those. Okay. In your notes, it's probably best to put using identities for sine A plus B, cos A plus B. Okay. And let's just check I've got all the brackets. So yeah, and I just need to close that off. I'll put a bracket in there actually. Sneak one in there. Okay. And that is it. That's it. That's your proof. Okay. Because what we're doing is we're multiplying these together, you see, and we're adding them together as well. Okay, you see how that works? Yeah, it's kind of neat. Okay, and it kind of does both at the same time. You see, by multiplying these, yeah. So you can see the modulus of all of that is going to be R1, R2, and the argument of all of that is just theta 1 plus theta 2. You see, so that's kind of nice. Okay, you can do a similar one for dividing. If you do Z1 divided by Z2, you just do that divided by that. A little bit longer. Okay, you've got to realify the denominator. Okay, but then you should end up with, I'm sure you'll know, R1 over R2, and then using the identities, you'd have cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay, really nice. Now, let's try a different one. Okay, that's my favourite one, because I love the mathematics involved, you see. So, you know, I do like trigonometry, has to be said. And there's no calculus in this. Yeah, complex numbers is okay. It's a nice topic. But I do prefer calculus and trigonometry. Truth be told, and graphs. Yeah, I love a bit of graph sketching as well. What's the alternative? Polar form or Euler form. Kind of the same thing, but yeah. Polar form is just a reference to polar coordinates, of course. Yeah, and Euler form is just reference to the wonderful Euler. Okay, so R1 e to the I theta 1, R2 e to the I theta 2. Can see how this works? It's so simple, really. So Z1 Z2 is equal to R1 R2 e to the I theta 1 e to the I theta 2 equals R1 R2. You see what to do with these? Yeah, e to the I theta 1 plus I theta 2. Don't really need that line, but I'll put it in anyway. E to the I theta 1 plus theta 2. Much quicker. Very simple as well. It's actually even easier to prove the division rule, okay, when you do this. Okay, so you know, I can just put it on down here. So Z1 over Z2 is equal to R1 over R2, and then you've got e to the I theta 1 divided by, which is the same as multiplied by e to the negative I theta 1. No, theta 2. I guess it wasn't a huge error. Okay. R1 over R2 e to the I theta 1 minus theta 2. Done very quick, but absolutely lovely. Okay, but it's a lovely proof demonstration that when you multiply two complex numbers together, multiply the moduli and add the arguments. Okay, and divide into complex numbers together, you subtract the arguments and divide by the moduli. Okay, hope you enjoyed that.